So, let's talk about trust. In a world where everything is digital, how do we actually prove anything is real? I mean, when you can copy and paste and change data with just a click, how can you be sure something is authentic? Well, today, we're diving right into the heart of that problem. Right. Think about it. Your real-world signature is unique, right? It's all about the quirks of your handwriting. But in the digital world, a 1 is just a 1 and a 0 is just a 0. They're all identical. So here's the big question. How do you create a digital signature that's impossible to forge, one that you can't just copy from one document and paste onto another, a signature that proves that you, and only you, signed off on that specific message?
The solution, as it turns out, is some seriously clever math. It's something called a digital signature. And we're going to get specific, looking at the exact method that secures huge networks like Ethereum. It's called the elliptic curve digital signature algorithm. Yeah, I know, it sounds like a real mouthful, but trust me, the ideas behind it are actually pretty elegant.
Okay, so before we can build this unforgeable signature, we need to get our tools together. And it all starts with a secret that only you will ever know. First up is your private key. Don't let the name fool you. It's not as complicated as it sounds. A private key is really just a huge, massive number that you've picked completely at random. And the most important thing, you have to keep it a secret. No one else can know it. This number, this is the key to everything you do. So, we have our secret number. Now we need a place for it to work its magic. And that place is the elliptic curve. Now, don't get hung up on that equation on the screen. All you need to do is picture this curve as a kind of mathematical playground. It has a very specific shape and a clear set of rules for how you can move around on it.
So how do we use these tools? Well, we use our secret private key to create a public key, something we can share with the world. Here's how it works. Everybody starts at the exact same spot on the curve, a point we call G. Now, remember your secret number, your private key? That number tells you how many times to jump along the curve from that starting point. And the final spot where you land, that's it. That's your public key. And this right here is the absolute magic of public key cryptography. It's what's called a trapdoor. It's super easy for you, with your secret private key, to figure out your public key. But for anyone else, trying to look at your public key and work backward, figure out how many jumps you made to find your private key, it's basically impossible. The numbers involved are so astronomically large, you just can't do it.
All right, so we've got our secret key and we have our public identity. Now for the main event, how do we actually sign something with it? Let's put that secret to work. Now, signing is another really slick mathematical move. You take your message, you create a unique fingerprint of it called a hash, and then you combine that hash with your secret private key. The result of that combination is your digital signature, a totally unique marker that is tied directly to you and to that very specific message. Change one letter in the message, and the signature becomes completely different. Of course, a signature doesn't mean much if nobody can check it. So how does the rest of the world look at what you've signed and know for sure that it was you, without ever getting a peek at your secret key? This is the key difference. To create a signature, you have to use the secret, your private key. But to check it, all someone needs is the stuff that's public, your public key, the message itself, and the signature you created. They plug all that into a verification formula, and what comes out isn't another secret. It's just a simple answer. Yes, this checks out, or no, something's wrong here. And that's the principle that makes this whole thing so powerful. The verifier can mathematically prove that whoever owns the secret private key is the one who created the signature. It's proof of ownership without ever having to reveal the secret itself. It's like proving you have the key to a house without ever having to show the key. But here's the thing. This system, for all its brilliance, has some odd little quirks. And hidden deep inside the math of that elliptic curve is a really strange one, and it can be dangerous. It's called signature malleability. So to get this, we just need to look one level deeper. A digital signature isn't just one number. It's actually made of a pair of numbers. To keep things simple, let's just call them R and S. So when you sign something, your wallet generates this R-S pair. And this is where things get weird. Remember that elliptic curve playground? Well, because of its perfect mathematical symmetry, it turns out that if the signature RS is valid, then a completely different signature is also valid for the exact same message. You can keep the R value the same, but you can mathematically flip the S value to its opposite on the curve. And guess what? Both of them will pass the verification test. So, why is this a big deal? Well, imagine a system that sees your transaction with one signature and blocks it to make sure it doesn't get spent twice.
An attacker could just take that same transaction, use the second valid signature, and broadcast it again, and it would sail right through. This just goes to show you that digital trust isn't magic, it's math. And developers need to know about these weird little rules to build systems that are actually secure.
And that leaves us with a pretty fascinating question, doesn't it? The math that secures our digital world is incredibly powerful, but it's also got these hidden corners and non-obvious rules. If the very foundation of an unforgeable signature can actually be, well, forgeable in a way, it makes you wonder, what other strange, subtle rules are quietly running the show, governing the trust and security of our entire online world?